Good afternoon, everybody. Welcome to the Initiative on the Digital Economy's Lunch Seminar Series. This is the first of our strange back-to-school term, but for the next couple of months, we will have our usual weekly lunch seminars with a group of really interesting speakers, both from MIT and beyond. I'm David Verrill, the Executive Director of the IDE. We're going to run this in webinar format, but please use the chat to pose questions. If there's a clarifying question, we may interrupt the speaker as we go, but we'll probably save most of them for the Q&A period. Behind the scenes of this series of seminars are a number of people that help make this happen. I want to acknowledge Jovi Caney and Carrie Reynolds for taking care of all of the logistics and getting us set up. And particular shout out to Dave Holtz, who's put together this fall semester's program. One of the duties and responsibilities of our best PhDs in the program. So Dave, very much appreciate the role you've played in putting together an awesome lineup of speakers. And why don't I share the podium with you to introduce today's speaker.
Great, thanks, David. So I'll just quickly introduce Dean, and then I'll let him get started. So Dean is a social scientist and statistician at MIT. Dean is the Mitsubishi Career Development Professor and Associate Professor in the MIT Sloan School of Management and affiliated faculty at the Institute for Data Systems and Society. He was previously a scientist at Facebook and Nokia. Much of his research examines how interactive technologies affect human behavior by mediating, amplifying, and directing social influence, and statistical methods to study these processes. Dean's empirical work uses observational studies and field experiments involving hundreds of millions of people. His published papers appear in proceedings of the National Academy of Sciences, Journal of the American Statistical Association, Science, and other peer-reviewed journals and proceedings in statistics, computer science, and marketing. Dean completed 5 degrees, including his PhD at Stanford. I'll hand it off to Dean, and I'll also ask that if everyone else is on mute during the talk, that'd be great. All right, thanks.
Okay, so yeah, it's my pleasure to talk to you all today about targeting intervention in networks and in business settings, and I think I'll try to share a couple interesting examples of how we try to target different interventions, increasingly based on lots of rich data about customers. And so I'm happy to take some questions throughout if they seem kind of timely with what I'm talking about, but also we have some discussion at the end. I'm going to discuss a couple different papers, but there's going to be a lot of emphasis on some of our collaboration with the Boston Globe, a collaboration that a lot of the really heavy lifting work of that has been done by a PhD student of ours who's on the job market right now, Jeremy Yang. So what I'm going to talk about first is just kind of the basics of how we should try to target interventions, and that we're going to target those interventions based on the effects that they have. And then I'm going to get a little bit more into some of the more challenging versions of that often we want to do targeting based on long run effects, not just short run effects of interventions. And then finally, depending on how much time we have, I'll also talk about targeting in networks. When people are connected by a social network, maybe we should use some of that network information to try to target our intervention. Okay, so the big question here is going to be, we have some intervention. This could be a targeted discount. This could be an ad. This could be a new version of a recommendation system. Who should we target with this intervention? Okay, so in our particular case, we were collaborating with the Boston Globe to help them retain their subscribers. And so some of the interventions looked like this. This is an email that was received in the first experiment that I'm going to talk about by people who are in treatment that gave them basically, without any particular prompting or effort on their part, a discount to their subscription price, with the expectation that for some people, this might prevent them from churning and help retain them as a subscriber for longer, okay? So that's an example of one intervention here, and you can kind of already see that it's going to be important to target this intervention, right? For people who are not going to churn, who are going to remain customers, offering them a targeted discount is going to be sort of mistargeted, right? It's going to reduce the revenue that you receive from them. So that's certainly a case where you wouldn't necessarily want to hit everyone with this discount. This is something that increasingly people are noticing in practice in CRM and in churn management, right? So a lot of times people historically would just think about the idea that we should target interventions designed to get people to not churn to those people who are at highest risk of churn, right? So we could have some predictive model that predicts who's going to churn and just target those people who are very likely to churn. But this doesn't always work so well. So here's an example from a study by Eva Escarza from Harvard, looking at a membership organization in North America. And here, each of these buckets on the x-axis is customer groups that are determined by a risk score for their probability of churning, with the low-risk customers on the right. So now if we imagine targeting just the high-risk customers, those people who are on the left with our intervention, it turns out actually in this case, the treatment increased churn. So treatment effects need not be so associated with the actual churn risk. In fact, the subgroups that seem to have a positive, that is reducing churn rate effect, are customer groups that are not necessarily those with the highest risk of churn. This similarly shows up in another application of hers to a wireless service provider in the Middle East, where we see that, yeah, in this case, the treatment is reducing churn rate across most deciles of churn risk. However, these treatment effects are not necessarily largest for the highest risk groups. So I think, one of the conclusions here is that we should really focus on trying to target interventions based on the effects that those interventions have, not just some baseline measure of risk. And typically this is going to involve some kind of iterative experimentation process of some kind. Okay. And so that's what we're going to do here, and we'll get into some various details and elaborations on this. But to give you a sense of what I'm talking about, here's kind of a simple version of the approach that we have in mind, which is based on data from an experiment where you randomly treated some people and some people are randomly in control, we're going to fit two predictive models of the outcome, whatever we care about. So that outcome might be long-run retention, or it might be some kind of discounted revenue over time, right? So we have one model for the treated customers and one model for the control customers that predicts based on their baseline characteristics, their covariates, their features, whatever you want to call that. It's going to predict their outcome. And so that means that for any given new customer, we can get predictions of what they would do in treatment and what they would do in control. Then we can just compute the difference in those two predictions. And that's our predicted treatment effect for that individual I. So that's, we're calling that here delta I hat is our prediction of the treatment effect for individual I. And then our targeting rule would just be to assign customers to treatment if delta I hat is large enough. If somehow the treatment is costless itself, or we've already incorporated the costs into how we define the outcome, like that it is profits, then we would just treat them if this delta I hat is greater than 0. So this is a kind of very simple approach to thinking about the problem of targeting from the perspective of treatment effects and the causal inference approach to the problem. Okay. Sometimes this approach here is called outcome regression because we're fitting a regression model predicting the outcome. Sometimes it's called a T-learner. Sometimes, confusingly, it's been called a direct method. In other cases, it's been called an indirect method. So, so not totally sure what to call it, but we're going to do something. So, yeah, it's my pleasure to talk to you all today about targeting interventions in networks and in business settings. And I think I'll try to share a couple interesting examples of how we try to target different interventions, increasingly based on lots of rich data about customers. And so I'm happy to take some questions throughout if they seem kind of timely with what I'm talking about, but also we have some discussion at the end. I'm going to discuss a couple different papers, but there's going to be a lot of emphasis on some of our collaboration with the Boston Globe a collaboration that a lot of the really heavy lifting work of that has been done by a PhD student of ours who's on the job market right now, Jeremy Yang. So what I'm going to talk about first is just kind of the basics of how we should try to target interventions, and that we're going to target those interventions based on the effects that they have. And then I'm going to get a little bit more into some of the more challenging versions of that often we want to do targeting based on long run effects, not just short run effects of interventions. And then finally, depending on how much time we have, I'll also talk about targeting in networks. When people are connected by a social network, maybe we should use some of that network information to try to target our intervention. Okay, so the big question here is going to be, we have some intervention. This could be a targeted discount. This could be an ad. This could be a new version of a recommendation system. Who should we target with this intervention? Okay, so in our particular case, we were collaborating with the Boston Globe to help them retain their subscribers. And so some of the interventions looked like this. This is an email that was received in the first experiment that I'm going to talk about by people who are in treatment that gave them basically, without any particular prompting or effort on their part, a discount to their subscription price, with the expectation that for some people, this might prevent them from churning and help retain them as a subscriber for longer. Okay, so that's an example of one intervention here, and you can kind of already see that it's going to be important to target this intervention, right? For people who are not going to churn, who are going to remain customers, offering them a targeted discount is going to be sort of mistargeted, right? It's going to reduce the revenue that you receive from them. So that's certainly a case where you wouldn't necessarily want to hit everyone with this discount. This is something that increasingly people are noticing in practice in CRM and in churn management, right? So a lot of times people historically would just think about the idea that we should target interventions designed to get people to not churn to those people who are at highest risk of churn, right? So we could have some predictive model that predicts who's going to churn and just target those people who are very likely to churn. But this doesn't always work so well. So here's an example from a study by Eva Escarza from Harvard, looking at a membership organization in North America. And here, each of these buckets on the x-axis is customer groups that are determined by a risk score for their probability of churning, with the low-risk customers on the right. So now if we imagine targeting just the high-risk customers, those people who are on the left with our intervention, it turns out actually in this case, the treatment increased churn. So treatment effects need not be so associated with the actual churn risk. In fact, the subgroups that seem to have a positive, that is reducing churn rate effect, are customer groups that are not necessarily those with the highest risk of churn. This similarly shows up in another application of hers to a wireless service provider in the Middle East, where we see that, yeah, in this case, the treatment is reducing churn rate across most deciles of churn risk. However, these treatment effects are not necessarily largest for the highest risk groups. So I think, one of the conclusions here is that we should really focus on trying to target interventions based on the effects that those interventions have, not just some baseline measure of risk. And typically this is going to involve some kind of iterative experimentation process of some kind. Okay. And so that's what we're going to do here, and we'll get into some various details and elaborations on this. But to give you a sense of what I'm talking about, here's kind of a simple version of the approach that we have in mind, which is based on data from an experiment where you randomly treated some people and some people are randomly in control, we're going to fit two predictive models of the outcome, whatever we care about. So that outcome might be long-run retention, or it might be some kind of discounted revenue over time, right? So we have one model for the treated customers and one model for the control customers that predicts based on their baseline characteristics, their covariates, their features, whatever you want to call that, it's going to predict their outcome. And so that means that for any given new customer, we can get predictions of what they would do in treatment and what they would do in control. Then we can just compute the difference in those two predictions. And that's our predicted treatment effect for that individual I. So that's, we're calling that here delta I hat is our prediction of the treatment effect for individual I. And then our targeting rule would just be to assign customers to treatment if delta I hat is large enough. If somehow the treatment is costless itself, or we've already incorporated the costs into how we define the outcome, like that it is profits, then we would just treat them if this delta I hat is greater than 0. So this is a kind of very simple approach to, thinking about the problem of targeting from the perspective of treatment effects and the causal inference approach to the problem. Okay. Sometimes this approach here is called outcome regression because we're fitting a regression model predicting the outcome. Sometimes it's called a T-learner. Sometimes, confusingly, it's been called a direct method. In other cases, it's been called an indirect method. So, so not totally sure what to call it. But we're going to do something slightly more elaborate than this. But this is kind of the basic idea that maybe we'll fix how to think about what we're doing. So, a little bit more formally. We could say that for each unit, such as a customer, we observe some of their characteristics. And so, for a given customer I, we observe characteristics xi, and then we're going to choose some action to take. So we have some available space of actions, and then we're going to choose a particular action. For the action that we choose, we get to observe their outcome, right? Whether they churn after some amount of time, how much revenue gets attributed to the customer. And a policy is going to be a way of making these choices about actions. So a policy is just a rule that maps from these characteristics to the actions. Now, some policies are deterministic. So it's just going to say, okay, if you have these characteristics, if you're in this zip code, we're always treating you, right? Other policies might be randomized. And so maybe a conditional probability distribution over the possible actions. So in this kind of a framework of policy learning, then targeting is simply a matter of finding a good, or perhaps the best, policy within some space of policies that we're entertaining, right? So what policies we can use is gonna be constrained by what X's we observe, what things we know about the customers. And it's also maybe going to be constrained by some desire for simplicity or interpretability, right? We might want a policy that we can explain within our organization. And so we're trying to find some policy, pi star, that maximizes the expected outcome given how we assign people to actions. And so we're going to do this using past data, ideally where we've randomized the actions taken in some way. Right? And essentially, this data that I showed you earlier from this Eva Escarza's experiment kind of fits this idea, right? She conducted an experiment in collaboration with this wireless service provider where they randomly assigned across all their customers, some of them to receive this treatment. Now, this can be a little bit wasteful as a starting point. We haven't tried interventions like this before, and when we were working with the Globe was not doing proactive churn management before we started collaborating. So they didn't have any data from randomized experiments with interventions of this kind. So we needed to run some sort of an experiment, right? So who should be included in these experiments, right? So our thought was, yeah, we don't know that somebody's predicted churn rate is going to be really closely connected with their treatment effects. But it's true, if somebody's very unlikely to churn, it's hard for there to be a benefit of giving them a discount. So in some sense, the benefit is really upper bounded by somebody's churn rate. So if somebody is going to stick around, then maybe they should not really be included in the experiment with high probability. So the idea is to sort of use something that we know about this problem, but also add a bit of exploration. And so in our first experiment, essentially we had a predictive model we built predicting probability that somebody was going to churn. And then people who had a higher probability of churn, we assigned them to treatment with a higher probability. Whereas people who had a lower probability of churn, we assigned them to treatment with a lower probability. So this allowed us to explore across the space of all customers, but not spend our time giving discounts to people that we had ex ante reasons to think this wouldn't be effective with. Okay, so you can think of this experimental design as kind of reflecting our prior belief about the imperfect relationship between churn risk and treatment effects. And so this, what I've just described, is the first of 2 experiments that we conducted that I'm gonna talk about here. This first experiment, we just had this single discount treatment, and then you'll see in a second larger experiment, we actually try a whole bunch of different treatments as well. So it's not just a matter of binary targeting who to treat, who not to treat, but actually also you know, what treatment each person should get. So, okay. So what did it look like when we went ahead and treated people? And all the results I'm going to show you account for the fact that people have different probabilities of treatment. So I'm not going to go into the technical details here today. The paper that this part is based on will be online shortly as a working paper. And happy to take questions following up about that. But all the analysis we're doing is going to be using so-called doubly robust estimators that are somewhat more sophisticated than this kind of simple approach I showed earlier, but have the same general idea, but can be more statistically efficient. Okay. So what do the results from our experiment look like? So here is a graph of the survival probability, that is the retention rates of customers as over time in people who are in treatment in the black line, the black dashed line, and people in control in the gray line. And this is accounting for this sort of unequal probability of assignment. And this vertical dashed line is showing when the discount that's offered by treatment ends, right? This was a 4-week discount. So we kind of really expect that it's going to decrease churn, at least for those 4 weeks. Kind of the question is it going to continue on after that, right? So overall, we see that this, for at least some time into the future, right, over a year into the future, this is resulting in higher retention rates for those people who are treated. On the other hand, this was costly because we gave people a discount. So we want to look at this overall in terms of revenue. The other challenge about this plot is this plot assumes that we've waited a really long time. Maybe for academics, this doesn't sound so bad. Waiting 510 days since you started a field experiment, right? I mean, the publication process in academia takes a long time. But for people actually making decisions, this isn't so great, right? The idea that in order to decide whether this treatment was effective and who I ought to target with this treatment, I need to wait so long, right? That doesn't seem very appealing. So how could we go about making decisions, not just about this treatment overall, about should we roll out this intervention in general, but improving the targeting of this intervention if we only had data from, say, the first 90 days? Is that something that we can do? So that's kind of what we study here, is how can we do targeting based on long run outcomes, right? Certainly one solution is to just wait, but that's kind of really limiting the pace that an organization can move at. Another kind of approach is to try to find particular sorts of proxies or surrogates for the outcomes that we really care about. This is something that's long been common in the context of clinical trials, right? So in a clinical trial, we might care about all-cause mortality at 5 years. Are more people surviving overall, right? But do we have to wait 5 years? And also, our patients might be dying for lots of different reasons, right? And so that could be a very noisy indicator. Even if we're willing to wait, it might be very hard to detect effects on that outcome, right? So instead, we might use things like other proxies or surrogate endpoints, such as hospital readmittance, all-cause mortality over a shorter period, or some specific measures of disease progression or something like that. And in some cases, you can actually really get quantitative data about how good different surrogates are. So here's an example with a number of clinical trials for leukemia. And so what we have on the x-axis is the estimated effect in that clinical trial on a proposed proxy, which is basically a leukemia-free survival. So it's a measure of, has leukemia gone into remission? And so it's one of these kind of disease-specific progression-free survival measures. And then on the y-axis, we have the measure in that clinical trial of this overall survival rate over a longer period of time. Okay. So actually, each one of these points here corresponds to one clinical trial in a country, right? And we see that a lot of the heterogeneity in the estimated effects on the outcome we actually care about does seem to be explained by heterogeneity in this in the effects on the proxy. So this might make us confident this is a good proxy. Similar kinds of things can come up in business settings. So here's an example from some of my own research. Here, in this case, sort of like the previous slide, each point is like a clinical trial, but here each point is a randomized experiment conducted at Facebook. Each point is around 20 million observations. And so on the x-axis, we have the effect of that experimental condition on one variable, and then the effect on another variable that we might think of as more an outcome that we care about on the y-axis. And so these two things are correlated, so this might make us somewhat comfortable that sometimes we could use this x1 as a proxy, though it kind of seems like there's a lot of outliers here. There's a lot of variation in how well x1 is actually predicting the effects on y. So often we might want to try to incorporate many such surrogates, either informally. Decision makers will often look at multiple surrogate variables, or we could do so formally and try to come up with some full set of surrogates that explain all the variation in outcomes that are caused by our actions. Okay. And so what conceptually that looks like is that we're taking some actions A that are affecting what we really care about, Y. Now, one of the ways that this might work is that it's affecting Y via some short-run changes, right? So in our Boston Globe example, the way it's affecting the long-run revenue and profits and retention, et cetera, is by changing short-run retention and also potentially by changing short-run behavior. Maybe it's making people say, oh, I really should try reading the Boston Globe more often and see if I'm getting value from it. And so then people change their consumption behavior, right? And then they discover value in the product that they hadn't been appreciating previously, and that's going to increase their long-run retention, right? And so the idea is that hopefully there are not these direct effects of our actions on the long-run outcome, but rather that they're all mediated by these changes to these surrogates. At least this would be one way for us to be able to fill in long-run effects of our treatments by simply learning a model of how the surrogates are associated with the outcome from historical data, and then applying that to our new experiment before we actually observe Y. And that's what we're going to do here. I just want to quickly give you another example of this kind of surrogacy in practice. This is a nice example in the context of star ratings. So star ratings have a lot of problems just as metrics. So if you're a ride-sharing company or delivery company and you're relying on star ratings, there's just so much customer heterogeneity in how people are using star ratings, right? I think I've had Uber drivers tell me, they, are, picking up some people or other people, that they may get lucky, they may not get lucky, right? So there's a lot of variation in that. And also the star ratings can pick up all kinds of biases, right? So a rider might be biased against some kind of cultural ethnic category that the driver is in, and that gets reflected in the star rating, right? And maybe that's not great for providing feedback to drivers, right? So there's selection, there's discreteness, people aren't really using the full range of ratings, like so many ratings on Uber are 5-star ratings. And so it's not really helping us discriminate between good driving and bad driving, right? So in this case, even if we observe the rating, though we don't always, a lot of ratings are missing, we might think it's a pretty noisy measure of the outcome that we care about. And so instead, you could use some kind of a surrogate based on telemetry. So you could look at actually how fast or how slow is the driver driving compared with other people who drive on that same road segment. If they're driving on my little street here, are they driving sort of faster than people usually drive there, or are they driving slower than people usually drive there, right? And if you look at how that's associated with star ratings, you can see that actually sort of being in particular regions of this speed space is much more associated with having a positive rating, whereas somebody who is often, for example, having a lot of time where they're very slow, or a lot of times where they're potentially very slow because they're also not reaching a very high speed, then this is indicating some things about the star rating they've received. So this is an example of using a model to potentially, instead of actually giving feedback to drivers based on star ratings, you could give feedback to drivers based on predicted star ratings based on these surrogates, that is, this telemetry data. Okay. So in our context, what we're going to be doing is trying to fill in the rest of this curve over here by using a bunch of customer behaviors and other intervening variables that we can observe in some shorter period of time. Okay, so what do we observe? We observe graphics of these customers, a bunch of their account activities, things that turn out to be quite important, like when is their credit card expiration date, because that's when they may have to make a decision about whether they're really going to keep subscribing. They have to consciously consider that. What articles they're actually consuming, so how much value they're getting out of the product, and information about how much revenue we're getting and whether they've already canceled. Somebody who's already canceled, we kind of know that their revenue in the future is going to be likely be low. We can then use these on historical data to predict long-run 3-year revenue. And here's a plot on the right showing how well we can do in predicting this long-run revenue. And so as we use more and more months of data, right? If we just use 1 month of data, it might be much harder to do this than if we're using multiple months of data. We can actually get quite good at predicting this long-run revenue. This is just sort of a heuristic view of how good are our surrogates. We don't necessarily want to predict all the variation in long-run revenue, just as in the example with these star ratings. It's not that we want to successfully predict all the potential biases or noise that are in the ratings, right? What we really care about is predicting the part of the ratings that reflects driver behavior and perhaps our interventions that might affect driver behavior. Okay, so we've learned the surrogate model. Then this means that for each customer, we can predict what their long-run revenue would be. And now we're just going to do this policy optimization, this targeting, based on that predicted revenue over the longer term. And so here we've imputed this outcome based on this predictive model. And then we're going to evaluate our learned policy using these surrogates in terms of effects on 18-month revenue, even though the policy was learned only on either 1, 2, 3, 4, 5, or 6 months of data, right? We haven't yet waited for 3 years here, so that's why we're using 18-month revenue, even though our goal is to predict 3-year revenue. And so here, this is the value of this policy in terms of expected revenue per customer for a policy learned on a surrogate model for 1, 2, 3, 4, 5, 6 months. And so basically, except for month 1, we have a significant improvement over the status quo where people are not being treated with this discount. And actually, in some comparisons I don't show here, we also find that this learned policy learned using these surrogates is actually statistically indistinguishable from one using the full 18 months of revenue. So in this case, we're doing sort of just as well, at least to the degree that we can detect, as if we had actually seen this 18-month revenue, but we have not yet. Okay, so this sort of illustrates the idea of doing this targeting based on some model for long-run outcomes based on a notion of statistical surrogacy. Just to kind of give you a taste of then, where this project has gone next, we've really expanded the space of actions that we could take here, right? And so targeting can only take you so far if you don't have a great space of actions, right? If you're just trying the same old things, I think that can only provide so much benefit. A larger action space can really help. So we tried a larger action space first, where we essentially require customers to claim their discount. So just receiving the email doesn't give them a discount, but they have to claim the discount. And we also vary the quantity of the discount. And we also included a placebo email, essentially, where they actually just get a thank you. And then also a version where they receive a gift card, so it doesn't actually affect their subscription rate at all. And so this is a follow-on experiment, basically using a lot of what we learned in the previous experiment to target this experiment. As before, we want to use the information that we have, but we also continue exploring, treating some people that we think maybe we shouldn't treat, but so that we continue to have randomization that we can learn from. And so here, in terms of the percentage point effect changes on churn, there was a bunch of substantial heterogeneity here in class. In fact, some of the smaller discounts, that is larger prices, resulted in greater reduction in churn, which was really appealing because this is going to have broader effects for revenue. So, and obviously, then we apply this whole same targeting, policy learning machinery on this experiment as well, but I'm not going to go into that today. Cool. Okay, so that kind of wraps up this first project I wanted to talk about, and so that's the case of targeting for long-run outcomes without having to wait. I think another interesting problem, at least to me, is how to target using really complex data like social networks, right? A social network is actually a super high-dimensional object, right? For each pair of people, it encodes the fact of how those two people are related, right? So there's a huge amount of information in a network. How can you use that to target? There's actually multiple ways that we can use a network to target, right? I mean, one way is actually just based around homophily, or the fact that birds of a feather flock together. So it might be if your friends are interested in something, it's a good idea to target you with ads for those kinds of things, because you probably might be interested as well, because you and your friends are similar, right? We also may want to target to try to exploit some kind of social multiplier. So a classic example of this kind of social multiplier is in the context of get out the vote effects. And so here, this political scientist randomly assigned households to be contacted door to door, either with an encouragement to vote or sort of as an active control and encouragement to recycle, which was a sort of a way of checking who was actually going to answer their door or not, okay? And they looked at contacted and uncontacted people in each household. So the people who were contacted, I went to your door, I talked with you, encouraged you to vote. Okay, we'd expect some direct effect maybe on whether you get out to vote, right? And so, for example, this effect in, say, Denver, on the direct effect is that there was an 8 percentage point effect on actually getting out to vote, right? This is measured using public voter records later. But there's also the secondary effect of the treatment on other people in the household who were not the person who came to the door, right? So this suggests that there's a lot of potential for social spillovers in various kinds of campaigns, advertising campaigns, as well as political campaigns, that is, commercial advertising campaigns. And more generally, a lot of interventions in this space try to use some notion of peer influence or social pressure. So a very popular intervention in the space has been these social pressure mailings where that look like this. The early versions at least look like this, that they say, what if your neighbors knew whether you voted, right? And sort of reminding people that essentially whether you vote or not in the US is a matter of public record. And so then they send you this table of all of your neighbors by address and recent elections and whether they voted or not, right? And then with this blank for this upcoming election, right? So this is maybe going to explicitly involve some of this kind of social pressure, right? These mailings have been used a lot recently and gotten more sophisticated or ominous looking. Here's one, I think, used by the GOP in New Mexico, After all, voting is a matter of public record. And I think this is the other side of that mailing. When Democrats win the election and you didn't do your part to stop it, your neighbors will know. Your neighbor, I guess, is peeking out from her window. Here's another example from 2014. So especially when there's this social component to the behavior, we really think that it could matter who we target with an intervention if people are connected in a network, right? So here I've just highlighted, within this is a small village of rice farmers in China where researchers in collaboration with the government were trying to increase adoption of farmers insurance. So if you were trying to do that, who should you prioritize talking to with kind of an intensive training and understanding how this weather insurance would work? Do you want to talk to these two people highlighted in green? Do you want to target these people in blue? Do you want to target these households in red? Here, all the edges correspond to people's self-report of who they go to for advice about personal finance and farming matters, right? And so we might notice that these red households are households that a lot of people go to for advice. So we might think they'd be good people to target. One of the challenges in this is, networks are really complex information, and it can be very expensive to acquire this network information. Typically, unless you are working at Facebook or Twitter or et cetera, you don't have really a good free measure of the entire network structure, right? And so how valuable really is this information? I think that's one of the questions we can ask more generally about targeting is how much does our targeting policy improve based on adding different sorts of data, right? So there's a lot of work in computer science on how you find the optimal seed sets to target, given that you observe some whole network. But what if you don't have the network? One recent argument from some researchers at Stanford suggests that network information, at least under some models, is not worth that much. It's kind of worth just a few seeds more. And what they mean by this is that, say, rather than targeting K people with our ads or to be our brand ambassadors, et cetera, using a whole bunch of network information, why not choose slightly more than that people as seeds? Why not, instead of choosing K people, we choose K plus X people, but we just pick them entirely at random, right? Maybe perhaps with some kind of constraints on the demographic groups that we're willing to target. And a bunch of their results suggest that if you're willing to increase your number of seeds a bit, you can kind of do just as well as if you had done this more optimal targeting based on the network information. So this would kind of suggest that network information might not be that valuable. So just to kind of read this off here, this is the size of a cascade, a viral cascade that occurs in simulations on a Facebook network, given different numbers of seeds and different ways of picking them. This black line is the optimal way of picking the seeds if you sort of were omniscient. And then some of these other measures are other common heuristic approaches for picking seeds. But notably, this blue curve here is just picking them at random. And if you see, if we're willing to pick 12 seeds, we're kind of doing basically as well as optimal with 2 seeds, right? And in fact, if we're picking a substantial number of seeds, it's basically the same whether we're doing that or using one of these other centrality measures, right? So this might suggest network information is not so valuable. I think there are some key limitations to this in terms of the type of model of the network that they use, which I won't get into a lot of detail here, but I think this is an interesting idea, thinking about trying to formalize the value of network information. And so we explored that a bit more, especially in the idea that what if we don't need to measure the full network? What if we can do targeting in networks without collecting this entire network, which seems sort of counterintuitive, but it's possible to some degree. One of the ideas one can exploit here is the friendship paradox. So in any network with what we would call heterogeneous degrees, that is where different people have different numbers of friends, then on average, a node's friends have more friends than them, right? So this goes along with the idea that your friends are more popular than you are, your co-authors have more co-authors than you do. Your sexual partners have more sexual partners than you do. These are all things that are true on average in basically any realistic network. Here's an example from the Facebook network as of 2011. This is the number of friends an individual has. This 45-degree line would be the case if their friends had the same number of friends that they do on average. But in fact, up until you have a pretty large number of friends, at least for 2011 standards, the average of your neighbor's number of friends is higher than your number of friends. So this can suggest that actually all you need potentially is local network information in order to do targeting. You can pick a person at random and then pick one of their friends at random. You will have found somebody who's more central in the network on average without having to measure the whole network. You will have just sort of measured this very little part of the network. So this idea has been exploited in some public health marketing interventions. Here's some villages in rural Honduras that they were, these public health researchers were targeting with coupons for either multivitamins or water purification. And they did so using either this kind of one-hop nomination process or just random targeting, et cetera. And so, and at least in the case of one of the outcomes, adoption of multivitamins, this nomination strategy of picking somebody who's a random friend of a random person seemed to result in more adoption overall. I think the evidence here is still quite mixed, and I have a paper that shows that some of the evidence here is quite mixed, but I think this idea is very interesting. What can we do if we want to do targeting in a network, but without measuring the whole network? So in some of our work here, we consider two different ways you might access the network partially. One is spread queries, where you've basically seen past spreading events. So you seed a random node and see who eventually adopts. So maybe you've observed a bunch of prior things going viral on Twitter, right? Or you can cheaply seed one behavior. You're seeding with some coupons and then using that to figure out who you should pick as, you know, some sort of a brand ambassador, right? Another kind of query model here is what we call edge queries, where you would observe some random relationship and then repeat this, often through some kind of cascading process. So I talk to one person, ask them who some of their friends are, and then I go talk with some of those people and repeat this, okay? And this is often used in kind of sampling methods in the field. It can also be used in the context of scraping algorithms. If you are running a scraping algorithm on Twitter, right, you're gonna try to control how much of Twitter you end up having to scrape. So you're gonna be querying some edges and follow up some of them, but not all of them, right? So in a spread query, we'd see, say, this red node starts a cascade and we see who eventually adopts. This blue node starts a cascade, we see who eventually adopts. This darker blue node starts a cascade, we see who adopts. In edge queries, what we do is we start it at multiple points. We ask people to reveal some of their neighbors, and then we ask some of those neighbors to reveal some of their neighbors, and we repeat that over multiple queries. In order to, and we do this in a way that controls how many people in the network we end up talking to. In order to evaluate a potential seed point using this kind of data, what we want to do is look at in how many of these edge queries did we end up talking to that person. So say if we wanted to evaluate you know, one of these nodes right here, or how good of a seed is this person, or how good of a seed is this person here, we'd look at how many times across these different cascades we would end up talking to that person, right? And that's going to be an indication essentially of how influential they are. That would be the way we fix the first person in a seed set, and then we do some things to deal with redundancy there that are standard in this kind of seeding problem. You don't want to seed people who basically reach the exact same audience, so you need to spread them out. So I'll briefly show an illustration of this idea using some simulations on a university Facebook network. And so what we're going to do is run simulations of this spreading process and and choose our seeds using different amounts of network data. So first, using this kind of edge query idea, we then are looking at what's the spread size that we accomplish with different numbers of seeds, 2, 4, or 10. These are these 3 different lines, and querying different percentages of the network, right? And so we can see that we can already get pretty substantial improvements by only, say, querying 20% of the network rather than the entire network, right? And eventually, if you query a large fraction of the network, you're going to get to something that's kind of equivalent to having the whole network information, but there's some gains you can make even before that, right? The same idea applies in this seed query case. If we observe past cascades and we use those to do this seeding, we can also get some quick improvements. So even if we've only observed 30 past cascades, we're able to be targeting with 10 seeds very similarly to as if we were targeting using the whole network, right? So that's quite nice. Now, if you actually explicitly think about how these queries of the network are costly, then it's often going to be the case that the best thing to do is to not collect all the data about the network, but to collect some data about the network, right? So here, if we imagine that we got revenue per spread of 0.01, cost per query is 0.1, and a cost per seed, which is much more expensive, right? This may be hiring somebody to be a brand ambassador, et cetera, is 1. Then the mean profit is actually being maximized somewhere in the interior here. And this is going to be a common phenomenon in this case. And so we're able to more flexibly trade off, collecting more information with trying to reduce our costs in getting that information, especially since there's basically, as you can see here, diminishing returns from collecting more and more network information. Okay? So this suggests a kind of algorithmic approach with actually a bunch of provable results that I didn't discuss here at all, provable guarantees about how well this can do compared with the optimum, to this idea of exploiting something like the friendship paradox. So rather than just doing something like just talking to one person and picking one of their friends at random, we're talking to a few different people and then pooling that data and applying an algorithm on top of that. So at this point, I think I'll just go ahead and wrap up and say that I think in general, one should design experiments to incorporate our prior beliefs about treatment effects, but still be able to detect when we're wrong. That's what we did in a lot of this targeting work with the Boston Globe. We said, we think predicted churn is going to be a good thing to target people based on, but we're not sure because that's not how it always works out. So we want to explore a bit. And then we use those experiments also to learn about the long term. And part of how we did that is by having data that's valuable for targeting, right? One of the things that's changed in the favor of traditional publishers is actually that they have more data about how people are consuming their service. So the Boston Globe now gets to see which sections you're reading, and that can be helpful in forecasting these long-run effects. And then finally, you can also think about targeting interventions in social networks without having to necessarily measure the whole network, which frequently is costly or is not possible. So anyway, happy to have some discussion about any of these directions, and I think actually also my co-author Jeremy Yang for all the Boston Globe work is here with us, and so can answer the hard questions as well.
Of research leaders at the IDE as we've transitioned to Sinan Aral as the new faculty director of the IDE. So it's great to have Dean, Dave Rand, Renee Goslin, and John Horton as new leaders of research at the IDE. Secondly, Dean and Sinan and others are running the conference on digital experimentation in November. So if you're interested in submitting a paper for that event or participating, please reach out to me at your convenience. And lastly, a nod to next week's speaker. Zoe Cullen is assistant professor at Harvard Business School, and she's been doing a lot of research on the impact on jobs and work in the COVID environment that we find ourselves in. So we will post her title and abstract in the coming days, and look forward to seeing you, many of you, back here next Wednesday. Thanks again, everybody. Take care.